In the last video, we looked at the ordinary comparison test. In this video, we're going to continue comparing series to each other, this time with the limit comparison test. So the first thing we're going to do in this video is state what the test is, then we'll work through some examples, and I'll save the proof for the end. Okay, so here's the statement of the limit comparison test for infinite series. Suppose that an and bn are non-negative terms, and all of the terms b sub n are positive. Create the ratio a sub n divided by b sub n and compute the limit of that as n goes to infinity. If that limit exists and equals a finite real number, here called L, then both series behave the same way. Either they both converge or they both diverge. So the idea is that you have a new series, say that's a sub n, and it looks very similar to a series b sub n whose convergence or divergence you already know. Then if you compute this ratio and it exists and is a finite positive number, so it has to be strictly between 0 and infinity, then whatever you can say about b sub n, you can also say about a sub n. It's important here that the limit, I'm going to state it again, it's not 0, it's not infinity, it's a finite positive number. What's less important is where you put the series that you already understand. So you can put it in the numerator or denominator, that doesn't matter. Okay, so let's look at a few examples. For our first example, consider the series whose terms look like 1 divided by 2n squared minus 1. Okay, this isn't a p-series, but it looks a lot like a p-series. Maybe that minus 1 in the denominator isn't going to affect the convergence or divergence if I compare this to an appropriate p-series. So I would look at this expression and say, that reminds me a lot of 1 over n squared. It probably has the same behavior as that series. So what we can do now is set up a comparison between this series and the known p-series 1 over n squared. So we can say the limit as n goes to infinity of, let me put this one in the numerator. So 1 over 2 times n squared rather. I'm going to divide this by 1 over n squared. Okay, to simplify this fraction, let's multiply the numerator and denominator by n squared. And the denominator is going to cancel out, leaving us with the limit as n goes to infinity of n squared over 2n squared minus 1. This is a rational expression where the numerator and denominator have the same highest power. So the limit of this exists and equals 1/2. This number 1/2 is what we were calling L in the statement of the limit comparison test. Sorry, trying to fix my one there. So this is that number L. It's a finite positive number. So it's greater than 0, it's not infinity, it's a nice number. That means that these two series behave the same way. So since 1 over n squared is a convergent p-series, this new series, 1 over 2n squared, almost wrote 2 to the n again, 2n squared minus 1, converges by the limit comparison test. Okay, so that's the result of this test. You can see it wasn't too bad. This is often going to be the test that you might try if you have a series that looks kind of like a p-series. So anything that looks like it might reduce down to 1 over n to a power, the limit comparison test could give you an effective way of comparing this to a p-series test, and p-series convergence we know. Let's look at a similar example. In this example, we would like to analyze the series n squared plus 1 divided by 6n cubed plus n plus 4. This is not a p-series, and yet it feels like it might trend the same way as a known p-series. So here's what you want to do for this kind of situation. Take the highest power in the numerator and the highest power in the denominator. So let's compare this with n squared divided by n cubed, which reduces down to 1 over n. We know that this is a divergent harmonic series. Okay, so we are going to set up a comparison now by computing the ratio of the terms from our new series to the terms in the divergent harmonic series. So we can say the limit as n goes to infinity of n squared plus 1 divided by 6n cubed plus n plus 4. Dividing by 1 over n is the same thing as multiplying by the reciprocal. So times n over 1. Okay. You see why this works, because after reducing here, what's going to happen is that we're going to give the numerator exactly what it needs in order to have the numerator and denominator have the same highest leading power. And then we're going to be able to say that the limit of this quantity is the ratio of the coefficients of the highest powers, which will match. So that's why you want to take the highest power from the numerator, the highest power from the denominator. When you multiply by the reciprocal, you'll end up with the same highest powers. Okay, so just to write it one more time, this is the limit as n goes to infinity of n cubed plus n divided by 6n cubed plus n plus 4. And then the limit of this ratio is going to be 1 over 6. Once again, that is this number L, and it's between 0 and infinity. It's a finite positive number. That means that our comparison was a good one. So because we were able to do this comparison, get to a finite positive number, we know that this series has the same behavior as the series 1 over n, which diverges. So we can say that thus the series diverges. By the LCT, limit comparison test. I want to make a little remark here before we go on, and that's that if you look at my lower index for this series, I started at n equals 0. 1 over n is not defined when n equals 0, but that's okay. The first few terms in a series never matter. So what we could do is say, all right, well, n equals 0 is not a valid index for the harmonic series. Does this converge from n equals 1 onwards, in which case everything we've written down would be valid? Yes, it does by comparison, so this series converges too. So it's always okay to chop off the first few terms in a series because those first few terms don't affect the convergence. Now consider this example. I would like for you to try to work this out on your own. So looking at this, you might think that it's different because we have a square root, but it's really not. Focus on the highest power in the denominator. Forget everything else. What does this series look like? It should look like a p-series. So set up a comparison with the appropriate p-series, take the limit, in this case as k goes to infinity, and see if you get to a finite positive number. So go ahead and pause, and then I'll come back and finish the computation. Okay, here's what I'm going to do is look at the denominator and say that the most important behavior down there is the square root of k squared, which is k. So let's compare with 1 over k. That is the divergent harmonic series. So if I set up the limit of this ratio and I get to a finite positive number, we'll know that our new series diverges. Okay, so we want to take the limit as k goes to infinity of 3 over the square root of k squared minus k minus 2 divided by 1 over k. All right, let me write that over here as the limit as k goes to infinity of multiply by the reciprocal, and we get 3k divided by the square root of k squared minus k minus 2. How do we simplify this? I'm going to leave the 3 kind of in front. I'm going to take k and write that as the square root of k squared. The quotient of square roots is the square root of the quotient, so I can put this together into the square root of a fraction that looks like k squared divided by k squared minus k minus 2. So this will be the limit as k goes to infinity of the square root of k squared divided by k squared minus k minus 2. I forgot the 3 times 3. I'll just write that over to the right. Okay. As k goes to infinity, this limit exists and it goes to 1 because the numerator and denominator have the same highest leading power. The ratio of their coefficients is 1. The square root of that is 1. So the limit of the square root exists. It's going to be the square root of 1 times 3. Just writing square root of 1 so that you see what happens. The square root of 1 is, of course, 1. So this limit is 3. This is the number L for this example. It's a finite positive number, so our limit comparison test was effective. So the series diverges by comparison. Okay, so we use the limit comparison test with the divergent harmonic series to conclude that this new series diverges. This is a neat example. Let's analyze the series whose terms look like the sine of 1 over n. So I'm putting over here a graph of the function y equals sine 1 over x. You can see it oscillates close to x equals 0, but that's not relevant to our series because our series starts when we start plugging in the values 1, 2, 3, 4, etc. So for the values that the sine function takes on 1 over n, you can see that we are looking at non-negative terms. They are decreasing to 0. Maybe we have a chance at convergence. What we're going to do for this particular example is actually compare the terms in this series to the harmonic series once again. So I'm going to compare this, the divergent harmonic series. Being able to do this limit comparison test effectively requires you to remember a known limit about the sine of an angle divided by the angle as the angle approaches 0. Let me set up and compute the limit. So we want the limit as n goes to infinity of the sine of 1 over n divided by 1 over n. As n goes to infinity, 1 over n goes to 0. Let me make a substitution here. I'm going to let u equal 1 over n. I'm just going to rephrase this limit in a recognizable way. So let u be the quantity 1 over n. As n goes to infinity, u goes to 0 from the right. So this limit is equivalent to the limit as u goes to 0 from the right of the sine of u divided by u. This is a known limit. We often state this as an identity in a single variable calculus class. I have a video about this limit actually where we derive it with geometry. Geometry is the correct way to learn this limit for the first time, but if you forget it, you will get the right answer if you try to apply something like L'Hopital's rule here. But overall, you should hopefully know that this limit exists, it's recognizable, it actually goes to the number 1. That is the value of L for this comparison test. So what we can say is that the series whose terms look like sine of 1 over n diverges by the LCT. because we were able to successfully compare it to the divergent harmonic series with terms 1 over n. This example is going to be our last example before we look at the proof of the limit comparison test. So consider the series whose terms look like 1 divided by the quantity n raised to the 1 plus 1 over n. So, this activity is on limit comparison test. We want to think of something to compare this to. What could we compare it to? Well, you could guess the harmonic series because I didn't even intend for that to be the case, but that's been the effective series for the past few examples. It turns out that's also going to be what we compared this example to, because if you look at the 1 over n in that exponent in the denominator, 1 over n tends to 0. So maybe this is going to behave like 1 over n, the harmonic series. That's just one way to get to that series as possibly the right series to compare this one to. So that's where my mind would go. If I had no other ideas, I would say, let's compare this to 1 over n, because maybe it starts to look like that as n gets really large. Okay, so compare, once again, with the divergent harmonic series. This is going to be an advanced limit computation, meaning that I'm going to set up the limit in the usual way and start to take it. But as we take this limit, we will need to use techniques that we haven't seen before in this lecture. Hopefully you did do this kind of limit in earlier calculus problems, but I just wanted to give you a bit of a more interesting limit than, the first few examples where we just had rational functions. So let's do the limit as n goes to infinity of 1 over, I could actually write n to the 1 plus 1 over n as the quantity n to the 1 times n to the 1 over n. So that's just using exponent rules. Divide this by 1 over n. And what's going to happen is, dividing by 1 over n, could rewrite this as multiply by n over 1 if you want. This n will cancel with this n. That's what I'm trying to get to. So this will be the limit as n goes to infinity of overall 1 divided by n to the 1 over n. This is an indeterminate form. The base, n, is getting really large. So typically we think something getting really large and exponentiated is really large. But on the other hand, the exponent 1 over n is going to 0. And we often think something being raised to 0 is the number 1. So it's like, which is it? There's a bit of a balancing act that we have to consider when we try to take this limit as n goes to infinity. So here's how you want to evaluate this. Let me switch now to the language of functions so that I have a little bit more machinery. I can do extra operations on functions. So how about y? I'm basically going to stop writing n and start writing x with the idea that x is, say, greater than or equal to 1. I could write 1 over x to the 1 over x, but I think that's a little bit more concise if I write this as x to the negative 1 over x. It's the same expression. Okay, again, this is an indeterminate form as x goes to infinity. If y is x to the negative 1 over x, and this number is always positive, we can take the natural log of both sides. So the natural log of y is the natural log of x to the negative 1 over x. But by properties of natural log, this exponent can come down in front as a coefficient. So this is going to be negative 1 over x times the natural log of x. And I think I like that better written as negative natural log of x over x. Okay, pause there for a second. Yeah, let me pause, digest this. What do you think we're about to do? So we have this expression about the natural log. We've kind of gotten this into a more usable form than with this exponent with a variable being raised to a variable. So see what you make of this, and then I'll come back and finish. Okay, what we're going to do now is take the limit as x goes to infinity of this quantity. If that exists and equals a finite number, that tells me what the natural log of y is. So then I can figure out what y is. And then if that limit is good, we can apply that to our original limit with the sequence terms. Okay, so let's do this. Limit as x goes to infinity of, how about I write natural log of y? Well, what is the natural log of y? It's this expression. So this is the limit as x goes to infinity of negative natural log of x divided by x. This is also an indeterminate form, but it's an easier one to evaluate than what we started with. This is infinity over infinity behavior. So we just differentiate the top and bottom with L'Hopital's rule. So we've got L'Hopital's rule coming into this. This will be the limit as x goes to infinity of negative 1 over x divided by 1. As x goes to infinity, the numerator goes to 0, the denominator is 1, so this limit is 0. That tells me that the natural log of y tends to 0 as x tends to infinity. Thus, the limit as x tends to infinity of y is going to be e to the 0. So you exponentiate each side. So to get rid of the natural log of y, I would do e to the natural log of y. So I'm going to do e to the natural log of y, e to the 0. Okay, so you can imagine e to this equals e to that. All right, that tells us that the limit as x goes to infinity of our function y equals x to the negative 1 over x exists. It is the finite positive number 1. Actually, this is going to have the same limit as our sequence, or rather the ratio of our two sequences that we're comparing. That's n to the 1 over n. I've got exponents inside of denominators. So 1 over n to the 1 over n. So this 1 here is the L we were looking for. So my conjecture was right. It wasn't guaranteed because, again, everything here was indeterminate. So when I said, hey, maybe that 1 over n just kind of goes away, that wasn't necessarily going to be the case, but now we've shown that it is. So it turns out that this series can be effectively compared with the divergent harmonic series. And since when we set up the ratio of these terms to these terms, we got a finite positive number, we know that our series converges by the limit comparison test. Sorry, did I say converges? I meant diverges. Our series diverges by the LCT. Okay, so this was a bit of an advanced computation where I wanted to kind of remind you what to do for these kind of indeterminate forms where you have to essentially break off this exponent from the base. And how do we do that? We do that with natural logs. We are ready now to look at the proof of the limit comparison test. The proof of the limit comparison test is really neat, in my opinion. It relies on our understanding of the ordinary comparison test. So here's how it goes. Suppose that we're applying the limit comparison test. So the limit as n goes to infinity of the ratio of terms an over bn exists and equals L, where L is a finite positive number. So where 0 is less than L is less than infinity. I want to say what it means that this ratio approaches the number L. If it approaches the number L, then that means for large enough values of n, as these subscripts get larger and larger, this ratio is really, really close to the number L. How close? Let me try to quantify that. So there exists some threshold index, some subscript that I'll call capital N. So that for all indices little n greater than or equal to this threshold, now let me put it here, n greater than or equal to the threshold, the ratio an over bn is very close to L. In particular, it's situated between L over 2 and 3L over 2. Let me write that down. I'll write an alternative version of it as well. We can say less than or equal to, that's okay here. Less than or equal to an over bn is less than or equal to 3L over 2. That this inequality is useful follows from the fact that L is a finite positive number. So imagine L was the number 4. If this list of terms or this ratio an over bn is approaching the number 4, then if you go out far enough, the numbers are going to be between 2, so 4 over 2, and 6, 3 times 4 divided by 2. Right? So if you're limiting to 4, eventually you're going to be between 2 and 6 from that point forwards. This can be made a little bit more rigorous. If you're interested, you could set this up originally as the distance between the terms an over bn and this limit L can be made suitably small. So I can make this suitably close to the limit. And in this particular context, suitably small, I'm going to take to be the value L over 2. Less than or equal to. Okay, let's multiply all 3 parts of this chain of inequalities by the denominator b sub n. So thus for all indices little n greater than or equal to this threshold that I've fixed, it follows that L over 2 times b sub n is less than or equal to, and actually, you know what? Let me add in a 0 because we're going to apply the ordinary comparison test, and I'm going to make it look a lot like that statement. Everything here is positive, so 0 is less than or equal to L over 2 times bn is less than or equal to an is less than or equal to 3L over 2 times bn. Now we have a chain of inequalities relating sequences that we're comparing. Take a moment to look at this list here and revisit the ordinary comparison test. So I want to claim that an and bn must behave the same way. Why would that be the case here? So I'll come back in a second and finish the proof where we will apply the ordinary comparison test to this statement to conclude that an and bn either both converge or both diverge. Let me run through every possibility. So maybe an diverges. Let's consider that as our first case. So situation number 1, what if an diverges, meaning the series of terms that look like a sub n diverges? If the series an diverges, here I mean infinite series, then 3L over 2 bn diverges by the ordinary comparison test. However, 3L over 2 is just a scalar number. This is just multiplying all the terms b sub n. That never affects convergence if this is just a positive number. So if this diverges, then getting rid of that constant and going to bn, that also diverges. Okay, that takes care of one case. Let's do, what about if the series a sub n converges? Then L over 2 bn is smaller than something which is converging. So again, by the OCT, this converges. So, okay, let's write that. Again, by the OCT. And overall, that implies that just bn would converge because L over 2, again, is just a scalar multiple. All right, so that takes care of what we would do with this if we had information about the series a sub n. We're going to be able to make the same kind of statements for the series b sub n. So let's imagine that we knew that b sub n formed a series which diverged. So third case, if the series bn diverges. Then L over 2bn would also diverge. Because again, that's just a multiple. But now the terms a sub n are bigger than something which is diverging, but so by the OCT again, we know that the series of terms a sub n diverges. Okay, so that's another application of the ordinary comparison test. Let's wrap this up now by considering the case where the series b sub n converges. Now we're going to work with this right side. So if bn converges, then so does this multiple of bn. So then so does the series 3L over 2bn. But now the a sub n terms are less than or equal to terms which form a convergent series, and we are basically finished. So a sub n converges by the ordinary comparison test. And that finishes every possible hypothesis and conclusion that we need for the limit comparison test. So what we see is that if the limit as n goes to infinity of the ratio of an and b over bn exists and equals a finite positive number greater than 0, then an and bn must form series which behave the same way.